Okay, so last time we talked about the universal law of gravitation. Any two masses attract each other. The force just pulls the masses together, and the magnitude of the force, F magnitude, is minus capital G m1 times m2 over r squared. And so, in terms of the direction, it's attractive. Okay? Pulls masses together, meaning you draw a straight line but connecting the two masses, and this gets pulled. Okay, so this one here gets pulled to this one, and this one gets pulled to that one. Right? Does that make sense, everybody? All right, now what we're going to talk about is gravitational. Yeah. Oops. Oh, so very good, very good. Because I was anticipating what was coming later. There's no minus. The minus is absolutely not there. If you keep that, that's absolutely wrong. Okay. It's the magnitude of the force. There's no minus there. It has to be positive. If you want to know why I wrote minus, is because that's coming up just the same thing. Okay. So now, the gravitational potential energy, that's going to have a minus sign in it. Okay? So this is the force, there's no minus sign. But the gravitational potential energy. Okay, same picture, but this time we're talking about potential energy. The symbol for potential energy is capital U. So when we were talking about objects near the surface of the Earth, we talked about U is equal to, remember, mvy, where y is the height relative to some vectors. Okay. So now we are talking about general objects. What is the gravitational potential energy? Not necessarily near the surface of the Earth. So this mvy was actually just an approximation. It was an approximation that works when the y distance is small compared to the radius of the Earth. Because the radius of the Earth is thousands of kilometers, it's not a bad approximation. Okay. But this is going to be a more accurate formula. It will be minus, and this is really a minus. I'm not screwing this one up. It's a minus sign. It's a capital G, m1, m2 over r. Okay. Now I didn't forget a square here. It's really not r squared. It is 1 over r. 1 over r, not 1 over r squared. Okay? Now, if you're wondering where that formula comes from, you can think about the relation. Do you remember we were talking about the relationship between potential energy and forces, right? And then we talked about, if you take the derivative of the potential, you end up with something related to the force. There's some minus signs involved. Okay, it's the same deal here. If I take the derivative of this guy here, okay, if I take the derivative, let's say with respect to r, what is the derivative of 1 over r? It's minus 1 over, yeah, minus 1 over r squared, right? So that's how you connect from one to the other. Okay. And so that's the reason why it's 1 over r rather than 1 over r squared. When you take the derivative, you will end up with r squared. Okay, now, any questions about that? Okay. If you're wondering about the minus signs, how do you end up with minus signs? You have to take into account that f is going one way, r is going the other, so if you want to get plus and minus signs right, you have to keep track of that as well. Now, so that's the formula for the gravitational potential energy. Notice that there is a minus sign. So that's the convention. The convention is that as r goes to infinity, u goes to 0. Okay. But if you're not at infinity, if you're at any value, finite value of r, you get a negative one. Okay. And this reflects the fact that gravity is attractive. So it tries to pull things together. It tries to make them stick together. Go to R equals to 0 as much as possible. Okay, any questions about this? All right. Now, you might worry that at R equals to 0, this thing blows up in your face. So it's infinity. That's actually the nature of the question of what happens in a black hole. As objects really get close together, at the end, you get really large. What's going on there? Okay. So that's, well, the point is that if you have two objects, they really can't overlap each other. They start hitting each other, so you never really get R equals to 0. Okay, so at infinite separation, the potential energy is 0, but for any finite separation, the potential energy is negative. Okay. So now let's consider a satellite. So for a satellite, remember that's something orbiting a planet, typically Earth. Okay. So let's suppose now that M1 is the Earth. Let's say M1, that corresponds with Earth. And let's say M2 will be the satellite, or vice versa. Thank you. It doesn't really matter because the equation is symmetrical in M1 and M2. Okay. Okay, now, do you remember, well, let me remind you, last time we derived the speed of a satellite in circular orbit. Okay. How did we derive it? We said, okay, here's the Earth, and we have a satellite going around a circle, and it has some speed v, okay, and there's going to be here's the radius from the center of the Earth. There's going to be some pull due to gravity, right? And that pull due to the gravity, we said it's equal to, in magnitude, is g m times me over r squared. But it also has to give me the centripetal force, which will be equal to mv squared over r. You guys remember doing that? Okay. And so we set these equal to each other, and we solve for v. You can pretty much do that right now. You cancel out the m's, you cancel out one factor of the r's, and then you end up with the formula that v is equal to the square root of capital G, the mass of the Earth, divided by okay, so there's a typo in my notes, sorry. I put RE, that should be the radius at which the orbit is taking place. If you have a copy of my notes, then it's a little bit off. There should be a E on that. Okay? Any questions about this? That was the speed of the circular orbit. Okay, now, so let's calculate for a satellite going around an orbit the kinetic energy. Okay, so the kinetic energy of the satellite. Okay, what is the formula for the kinetic energy? It's 1/2 mv squared, so we call that capital K. 1/2 mv squared. But we have a formula for v. It's the square root of something. So getting v squared is kind of easy. You just get rid of the square root sign. So we will have 1/2 mv squared. So that will be the square of the square root means you rip off the square root sign, and you end up with 1/2. I'll have a G, I'll have an M, I'll have an ME, and I will have an R. Okay. Everybody all makes the front. Okay, now this looks kind of familiar, right? If I take a look at what is the potential energy, what is the formula for the potential energy? We just did that. It's minus G times the product of the masses divided by R. Ready to do that? Okay, that's the formula we had before. Okay, so it turns out that they are very similar to each other. Okay, I can write that the kinetic energy is always positive. So there's no minus sign here, but if I take U, take the minus sign off by multiplying by -1, and then I multiply by 1/2, I get K. Does everybody see that? Okay, so the kinetic energy ends up being -1/2 times U. Or if you prefer to go the other way, you can say U is equal to -2 times K. Questions? Questions? Okay, so that's actually a general formula that works for any orbit. It's kind of, you can actually derive this formula without doing all these steps. There's actually a way of doing that, but that requires learning about differential equations, which we're not going to go through here. Okay. Okay. So this formula is true for any orbit. K is -1/2 U, or if you want to think in terms of U is -2K. Okay. Now let's talk about the total kinetic, the total mechanical energy, adding up both together. So let's talk about the total mechanical energy. Okay, so that's E mechanical. That is going to be K plus U. Okay. Now, if I have K as -1/2 U, and I can replace it with -1/2 plus U, and so I end up with 1/2 U. And then as a result, I'm going to plug in the formula that I had for U. I get 1/2 minus 1/2 G M M E over R. Any questions about that? So if you have a satellite and it's orbiting around the Earth, this is what we call,
Isn't that just -K?
Yeah, you can write it as -K as well. Yeah, you can. There's many ways to write it. You can also write it as -K. 1/2 U and -K. Okay. So if you have a satellite going around the Earth, sometimes people will call this a bound system, or what they call a closed system. The satellite doesn't have enough energy to actually leave the Earth's orbit, because its energy its total mechanical energy is negative. In order to get way out in outer space, to be very far away, you have to just think about the formula for the potential energy. At infinite distance, it goes to 0. Okay? So if you're at infinite distance, or very, very far away, the potential energy is negligible. It's essentially 0. And then you have some kinetic energy, possibly, because you're moving. And that's always positive. So if you're trying to build a spaceship, Star Trek kind of a thing, or Star Wars, whichever you prefer, and you want to go very, very far away, leave the Earth's orbit, you want to leave the solar system, maybe even leave the Milky Way galaxy, right? So you want to have a total energy that's going to be positive. Because you want to be far away where gravitational potential energy is 0, but then you'll still have some kinetic energy, because presumably you want to be moving, right? What's the point of going to outer space and then being stuck in outer space and not moving? then you would have to have positive total energy. This is not going to give you that. If you have a satellite that's bound to the Earth, it will have a negative energy, total mechanical energy. Okay, any questions about that? All right, now let's focus on if you wanted to make a rocket so that you could actually leave the Earth's orbit, so you could explore space. And you might want to know how to build such a rocket. Right? By the way, I forgot, it's been a while. How many of you are aerospace engineers? Or, yes, really. Okay, so this is relevant to you. How much thrust you need in your rocket, what speed you need to make the rocket take off after it's burned all of its fuel. So let's consider a rocket. Okay, now we're going to say M is the rocket, and M2 is the Earth. Okay, so let's say now the rocket starts from the surface of the Earth, which is kind of a good assumption. Where else would it start from? Surface of the Earth. So if you want to know what that means your distance from the center is equal to the radius of the Earth. Okay. With initial speed v. Okay, you might be confused by that because before the rocket takes off, obviously it's starting from rest, right? But after it's dumped all, it burned all its fuel, it has some initial speed. Okay, it hasn't lifted off that far yet after it got its thrust. Okay, so let's say it has some initial speed v. Then we want to know how much v needs to be. Okay, so let's calculate the total mechanical energy. So you can tell your friends today you learned rocket science. Okay, so the total mechanical energy is K plus U. All right, now we're going to say the kinetic energy is 1/2 mv squared. Okay, and the potential energy will be the usual thing we wrote down. It would be minus g, the mass of the rocket. Let's just call it plain old m. Okay, the mass of the Earth is me, and divided by re. That's the radius of the Earth. All right, so we want this rocket to be able, we don't want the rocket to fail. We don't want it to go up and then come back down and crash. Okay, that's no good. We want it to have enough lift off so that it can keep going. Right? So we want the rocket to be able to reach infinity. That sounds kind of profound. So R equals infinity. Okay, so that means we need the mechanical energy to be positive. Zero would be enough, but 0 positive. So we need E mechanical to be greater than or equal to 0. Okay. So now, let's take this formula for the total mechanical energy. We want 1/2 mv squared plus minus g me over re to be greater than or equal to 0. So what I can do is I can bring this guy to the other side, and we'll have 1/2 mv squared is greater than or equal to g without the minus sign, me re. Okay, I can now simplify a bit. The m's cancel out. Positive number, there's no harm in dividing by it. And then let's multiply by 2. V squared is equal to 2 GE over RE. And then we can take the square root of both sides. That's perfectly fine. It means V must be greater than or equal to the square root of 2 GME over RE. Okay. This thing here is called VESC, the escape speed. Escape speed. Actually, they call it escape velocity, but technically it's speed because we didn't say anything about direction. Okay. Typically, people say escape velocity. So VESC is equal to the square root of 2GE mass of the Earth divided by the mass of the divided by the radius of the Earth. Take the square root. That is the escape speed. The minimum speed needed to escape Earth gravity. Okay. Any questions about that? All right. Good. Let's do a quicker question. This. Okay, so this is about 2 neutron stars. So these are exotic objects. They have about the mass of the sun, or even more than that in some cases. But they are really small. They're like tens of kilometers in radius, so they're tiny, but they're very massive. Okay, so you have 2 neutron stars separated by a distance of 7,600 kilometers from the center to the center. The 2 neutron stars. One has a mass of 1.5 times 10 to the 30 kilograms, and the other is 2.0 times 10 to the 30 kilograms. What is the gravitational potential energy of this system? And I'll open up the colon.
What's the value of G?
Oh, okay. Yeah. Okay.
Oh, great. Gives you kilometers. Let's see.
Okay, are people still working? I see some pencils still going. Okay. If you haven't made a choice, go ahead and make a choice in the next 20 seconds. All right, I'm going to close up the polling now. All right, let's see what people said. All right, it's a close one between B and C. All right. Okay. Let's take a look. Okay. So we have gravitational potential energy is minus G m1 times m2 divided by r. G is 6.67 times 10 to the minus 11 newton meters squared over kilograms squared. M1 is 1.5 times 10 to the 30 kilograms. M2 is 2.0 times 10 to the 30th kilograms. And the distance is 7,600 kilometers, which is 10 to the third meters. And so this comes out to minus 2.63 times 10 to the 43 joules. Okay. Any questions about this? Okay, the next thing we're going to cover is something completely different. So we are going to talk about motion that is related to motion on a circle. So we've been doing lots of things with circles. But the thing we're going to be talking about, notice when something goes around a circle uniformly, if I just keep track of how the vertical part of it looks like, it's some sort of an oscillation. Okay? All right? That takes some coordination. And that oscillation is actually what happens in nature very often. Okay? So first thing to start off, this is what's called, this is a mass on a spring, which we'll talk about a lot. All right? Typically, the simpler case is if the mass is on a frictionless table, but it's hard to actually get a frictionless table because it doesn't tend to want to move. Okay? So the easy way to do it is to make it vertical. The vertical is a little bit complicated in that now the relaxed position of the spring is not sort of here anymore, but it's over here. But the properties of the spring still hold. In other words, it has a different equilibrium length now. That's the relaxed position of the spring. It still has the same spring constant. If I pull an extra amount x, it will pull with the force minus kx. Okay. Maybe I should call it y since it's inversely. So it behaves just the same way. If I push it up a little bit, it pushes down. Okay. Gravity plays a little bit of a role in it. Okay, but the thing we want to understand is now, if I displace it a little bit away from equilibrium, it makes these oscillations. Okay? It's very much like, as I was showing with my fingers, it's like the vertical component of this circular motion. Okay? This motion is called simple harmonic motion. And so we're going to discuss that today. And pretty much, it's all about sines and cosine functions. Okay. Simple harmonic motion. Okay, simple, you know the word what simple means. The word harmonic, it means it's relating to sine and cosine functions. Let's start off with the basics. So, what does cosine of t look like? All right. So let's write t. Let's think of t not as time for the moment, but just as some unitless quantity. Okay. Otherwise, the cosine of something with units of seconds, that doesn't make any sense. But let's just take t to be just a plain number. And for a simple harmonic motion, we're going to be working in radians. We're going to be working in radians, all right? So if you're doing questions with simple harmonic motion and you have to take cosines and sines, the thing inside the angles will be measured in radians. So this is slightly annoying because everything else we've done, the angles are in degrees, so you're going to have to switch. Okay, if you don't want to switch, you can make the conversion as well, right? Everybody knows how to convert degrees. Okay. Actually, maybe not everybody does know. So the conversion is 180 degrees is equal to pi radians. Okay, so if you want to take ratios, you can say multiplying by 1, or maybe you want to go this way, pi radians, 180 degrees. Okay, that's equal to 1. Okay, but back to the question, what does cosine of t, where t is in radians, look like? It looks like this. And, by the way, you're kind of expected to know how to graph this. Okay? You're not supposed to not simply know how to recognize it, but actually, when I'm showing you, this is something you should be able to do. First of all, cosine t, here's t. First of all, it starts off at 1, because cosine of 0 is 1. Okay? And here's my plus 1. Here's a minus 1. All right, now let's go with pi over 2, pi, 3 pi over 2, 2 pi. Okay, here's pi over 2. Here's pi, 3 pi over 2, 2 pi. Okay, now with angles, going 2 pi radians is coming back to a full circle. It's doing a full circle. So then it will repeat itself. So a cosine of 2 pi will be 1 again. Now cosine of pi, let's think about that. That's cosine of 180 degrees. Anybody know what that is? Yeah, is it 0 or negative 1? Which one is it? Yeah, -1. Okay. So it's actually over here. Now, how about pi over 2? That would be 90 degrees. What's cosine of 90 degrees? So 0. Okay. What do you think then cosine of 3 pi over 2 would be? Yeah, also 0. Okay, so that's what it looks like. It doesn't make straight lines, but it has these sort of curves, right, where it has 0 slope here, and then it passes through here sort of straight, but then it has 0 slope again here. Okay, so it makes these like this sort of shape to it. And then you can continue it on like this. Any questions about that? Okay, so this is in radians. Now, what does a cosine of t look like? All right. Well, I'm just multiplying by a. Okay. So then, what it will look like is this. Okay, let's say a is a little bit bigger than 1. T is again in radians. And let's say this is now positive a. This down here is negative a. And we have again pi over 2, pi, 3 pi over 2, 2 pi. And it will go from positive a, I'm just stretching this by a factor of a. It'll go through 0, then it'll go to negative a, go through 0, and then go through positive a. It should be so spiky there. Okay? Any questions about that? That makes sense to everybody? Okay, so this a here, this when I write cosine a cosine t, this a is this a here is the amplitude. That's why I call it a. Call it the amplitude of the oscillation. So if somebody were to draw the oscillation versus time and were to ask you what is the amplitude of the oscillation, it's really a simple question. You just look at how high does it get? And that's the amplitude. Or how low does it get if you want, and it will be the negative of the amplitude. Okay. Any questions about that? Now, suppose we want to do something where we're really talking about an oscillation versus time. So we want, let's say we want the oscillation, to repeat after time capital T. And capital T is, we've already mentioned this before, this is called the period. Okay. So the period T is equal to time for one cycle. Once, complete oscillation. Okay, so I'm going to write down a slightly complicated formula and then show you that this is what we want. Okay, so note that if I write A for the amplitude times cosine of 2 pi over capital T times small t, this has the right period. Let me try to convince you of that. Okay. All right, so let t prime be equal to t plus the period. Okay? What I'm going to do is I'm going to evaluate this function not for t, but for t prime. All right? So let's evaluate a of cosine, a times cosine of 2 pi over capital T times t prime. And I'm going to then plug in t prime is small t plus capital T. And just see what happens, okay? We have a of cosine 2 pi over capital T, t plus capital T, like that. All right, is everybody still with me? I just wrote t prime, replace it with t plus the period. Now I'm going to multiply 2 pi over capital T to both of these. I'll just distribute them. Then I'll have cosine of 2 pi over capital T, okay, plus, now I have a capital T, and then I have capital T in the denominator. And so they will cancel, and I get plus 2 pi. Now, we said that we're measuring the angles in radians. So if I have an angle and I add 2 pi radians, I didn't change the cosine at all, because adding 2 pi is going around a full circle. Everybody agrees with me on that? Okay, so this is the same as not having the 2 pi. So that's just a cosine 2 pi over t, capital T times t. So what I've just shown is that a cosine for 2 pi over capital T prime is equal to the a cosine 2 pi over capital T. So in other words, t prime and t, whatever they're doing the same thing. Does that make sense to everybody? Okay, that's the definition of a period. If I shift by this capital T and I get the same function value, that's what a period is all about, when it repeats itself. Okay, so that's why this is cooked up to be perfectly the way you want. So if I write a cosine 2 pi over capital T times t, this has period capital T. Okay? So if I were to draw this function versus time t, right, then here's my a, positive a. Here's my negative a, amplitude. I have then like this, right? And this is the time when it repeats itself right here. And this is going to be the time, so that's just time. This is the period, capital T, when it repeats, okay? And this will be the period divided by 2, where it's negative of the amplitude. Right? And then this will be 1/4, if you want to get all of these things, 1/4, and this will be 3/4 of the period. Okay, any questions about this? Everybody's good on that? If you compare with what we drew before, the period before, when we had unitless t, that period was 2 pi for 2 pi radians. So that's how you match them, basically. Okay. If no more, any questions? All right, if no questions, I'll see you guys tomorrow.